So this is my whole design like I did as a student, like I said. So this is my graph paper. When you set it up on graph paper, we're gonna help you with scale. So see right here, I say that every 0.25 inches on the paper is equal to 3 inches in real life. You need a scale so that you can actually recreate it in real life the right size so we have a chance of following your path and getting an actual hole-in-one. The 0.25 inches comes from the fact that this graph paper had 0.25 inch squares literally on it, okay? Whether I scale it to 3 inches in real life, I'll help you guys with that when you're setting up your individual holes. Usually 2 or 3 inches works well for us to make it big enough for us to see on paper, but still fit on paper so that we can recreate it in life and not have to tape a bunch of papers together to draw our golf hole, okay? And so then I did the shape and everything like that. You guys are gonna have access to the graph paper. I'll provide it for you so that we're all using the same scale and stuff like that. And then you'll have access to a ruler and this special tool I'm gonna give you to help reflect the ball. So the one physical principle we're gonna use is that it says if a ball is traveling at a certain angle and hits a wall, it bounces off the wall and travels at the same angle, okay? So what that means is that like this angle right here is between the wall and how the ball went into the wall. And then when it bounced off of the wall and came back out this way, it should be at the same angle right there, okay? But I'm not gonna let you guys use a protractor. So you're not gonna be allowed to use a protractor to measure your angles, but I have like the outline of a protractor and a tool that we'll be able to use to just like, you know how you walk around your house sometimes and you're like, oh, it's that big, will it fit? Okay, but something that we can actually mark it and then just reflect it so you can draw the angle going the other way. So you'll have a tool that should be reflecting all of the angles, and then you'll be allowed a ruler. You can measure anything you want on the paper. So as a student, if I had done this, I found a path and used the tool to find a path that technically should follow this rule, and this would make a hole-in-one theoretically, okay? Obviously, real life, random things come into play and get in our way. Now, then what I did is I took my ruler and I went and measured the different lines that I drew on the paper. So for example, this line right here, this is a measurement of how long this line is right along here. Okay, and so that ended up being 5 9/16 inches, which is 5.5625 inches. We are using inches because part of the materials that I'm going to provide you with to build your golf hole, if you choose not to build it on your own, because you don't have to, I have supplies here that you can use to set them up, are in feet, not in like centimeters and stuff like that. So we need inches in order to convert that properly. So I then went through and just measured like the path of my hole-in-one ball traveling on my golf hole, how long each particular piece was. So the main part of the project is you proving to me that your design and your path makes sense because you used the tool correctly and you applied this physical principle that whatever it came in at, that angle is the same angle it left the wall at when the ball bounced, which basically means I want you to prove to me on here that angle, see, I'll highlight them so you guys can see that this angle that I called angle 1, the angle where the ball first came into the wall at, is the same as angle 2. That's going to prove to me, if you can show me that those angles are the same, that would prove to me that you did follow the physical principle and that you were able to use the tool right while you were building your hole-in-one and you didn't just fudge it to make it look like it works. Is that okay with everybody? So the math piece for me in your project is going to be the proof that those things are the same because I'm not letting you just measure it with a protractor. I'm only letting you use a ruler, which means you can measure the distances, but you somehow need to do some math with those distances to prove to me that the angles are the same. Okay, so how do we find angles if we can only have length measurements? We put those angles into a triangle, right? And we have trig that helps take angle measurements in a triangle and relate them to side lengths of a triangle. Okay? And so how you build triangles on here, this is the part that might be hard a little bit from your project. So here was the path of the ball. It came and hit the wall right there. Okay? Here's the wall. Those two things need to be included because that is the angle at which the ball hit the wall. It has to be between the path of the ball and the wall, okay? That's why I numbered that angle, angle number 1. That's what I'm finding. How do I put that angle into a triangle? I simply drew this dashed line right here because it basically connected them And it didn't just make any triangle, it made a right triangle. And the reason I know that it's a right triangle is because this drawing is on graph paper. And on graph paper, the grid lines are perpendicular to each other, right? And this line up here is along the grid lines one way, and this other line I drew is along the grid lines another way. So now angle 1 has been like inserted into a triangle in hopes that that can help me figure out angle 1. Is that okay with everybody? Right. I'm trying to prove that angle 1 is the same as angle 2. So I need to do the same thing for angle 2. So look at the pieces that made angle 2. It has to be the path of the ball. Here's the path of the ball leaving the wall itself. Those make angle 2. And what I did was connect them. And then that built a triangle around angle 2. Again, a right triangle because one of the lines in my triangle is going one way along the grid lines and the other way is going with the other grid lines. Okay, so is everybody okay with which angles I'm looking at on here? Okay, that our objective is to prove they're the same, and the way we're going to find the angles is by building little triangles around them. Okay, so this is the math piece that you're going to be doing in your project. So I'm now going to take these and I'm just going to redraw these triangles down below where it says classwork 3. Okay, so down here I had a triangle like this for angle 1. Just kind of sketching them. And then I had something like this for angle 2. I called this angle 1 and this angle 2, and my goal was to find them. Okay? Because I had a ruler, I can measure anything around angle 1 and angle 2. So some of these measurements are already given. Let's focus on triangle 1 first. Okay? So I'm going to go back. I'm going to look at what's on the paper for triangle 1. The things that have been measured around it is what I'm looking at. So I measured this length right here. We already talked about that 5 9/16 inches. So that portion of the triangle with angle 1 is 5.5625 inches. Okay, that's how long that piece is. Nothing else on here has been measured, and it wouldn't really be safe for you guys to measure it right now because you don't know if when I photocopied this and inserted this picture, it got like zoomed in or zoomed out, right? But another way to measure is if we look right here along this side, notice it goes from this point right here to this point right here. And we can literally count the number of squares, and we know that each graph paper square is equal to 0.25 inches. So this is 1, 2, 3, 4, 5, 6, 7. This line right here spans the length of 7 squares. And you guys have a calculator, so I don't want any complaints about the crazy numbers. Okay, so 0.25 used 7 times is 1.75. So that means this other side right here in the triangle surrounding angle 1 is 1.75. And again, remember, we know this is a right triangle. I could go find the third side if I wanted to too. I could count all the squares or get my ruler and measure it if I had the original paper. However, 2 sides in a triangle is enough for me to find the angle, right? Every trig equation needs 3 parts, an angle and 2 sides. We now have enough information right here that we have an angle, okay? And we have 2 sides. We should technically be able to set up a trig equation for angle 1, okay? What would these sides be called in this triangle? If angle 1 is our perspective, that's the one we're using to figure out things that are opposite, adjacent, hypotenuse. What would we call 5.5625? Which side of the triangle is that? Hypotenuse. Is everybody okay with that? It's across from the 90-degree angle. What about the 1.75? Adjacent, okay? So which trig equation do I want to use if I want to find this angle using the adjacent and the hypotenuse? Cosine. And are you guys okay? I'm not going to use 1 when I'm solving because I don't want 1 in there because that's confusing to me whether that's like a number or the name of an angle. So I'm just going to call it like momentarily like angle A or something. So the cosine of angle A is equal to the adjacent 1.75 over the hypotenuse. And how do I finish solving this? I actually had this question during tutorial several times today. How do we finish solving for an angle when it's the missing piece of the equation like this? The inverse cosine, okay? So angle A is going to be equal to the inverse cosine of that ratio. So that's what you would put into your calculator. And so when we put this in, we should get, let's see, 71.66. So we're going to use the nearest tenth. So we're going to call angle A 71.7 degrees. And I'm just going to keep track of this over here. So the measurement I found of angle 1 turned out to be 71.7 degrees. Okay. So right now we should feel kind of like we're doing those worksheets that we did for practice, right? Like once we drew them, we have these right triangles. So this is why we gave you guys the classwork and the homework that we gave you. We want you to get good at solving, but then the word problems kind of helps you draw some other random pictures, and that kind of mimics what your golf course is going to look like, that you're going to have to put together these pictures of these triangles. So we're going to go ahead now and then try to do the same thing finding angle 2, okay? So in the right triangle that surrounds angle 2 is going to be part of our equation. I'm going to call that B if that's okay with you guys. Again, it's just confusing to me to have a 2 in the equation that's not actually supposed to be the number 2. So I'd rather use a letter. And then we're going to look at what surrounds angle 2. Okay? And again, you would be taking these measurements on your paper. So the ones I've provided for you, this measurement right here says 3 3/8 or 3.375. So this measurement along this triangle is 3.375 inches. And again, you can use whichever ones you want, but I find it easiest in this diagram for me to use this portion here. And that portion takes up 4.5 squares. So to figure out what that is, I would be doing 0.25, because that's the distance of each square, times 4.5. Okay. And you guys have a calculator, so all of these calculations you should be able to do. Okay, so that should give you 1.125. And so that's the other measurement over here, 1.125. Again, you can go find the third one, but there's enough here. So that says 1.125. Okay, I know it's hard to see. That's that number. Okay. All right, so again, this turned out to be cosine. Am I saying throughout your whole project you're going to use cosine? No. It just so happened in these triangles, the things that were conveniently already measured for us or showed up happened to be the hypotenuse and, again, the adjacent side of the triangle. So our equation would say that the cosine of this angle is equal to, and we would set the adjacent over the hypotenuse. Okay? And we would find that angle by doing the inverse cosine, again, of that fraction. And so when we do that, we should get 70.52. So we'll call this 70.5 degrees. And so we found angle 2 and we got 70.5 degrees. Now you might argue that I just proved I didn't do this correctly. However, real life is a lot messier. So you're going to have a cushion for error in this project of 4 degrees. So as long as your angles are within 4 degrees, then I will consider that equal enough given real life, because you're going to be drawing this with your hand, even though you have a ruler and a tool to help you. You're then measuring it with the ruler yourself and writing down what that is. You're then using the sines and cosines and solving, and at some places rounding slightly. And so 4 degrees will kind of help all of those like error things that might show up, okay? So this would be good enough to prove that those two angles were equal. So for every ricochet in your project, this is where I said if you make like 10 ricochets, it might get a little messy. Every time the ball ricochets, you have to prove to me you used the tool correctly, which is to prove that both angles are the same. So you basically have this amount of work to do for every ricochet that you have in your project. I am requiring 2 bounces. I think that's a fair amount of work. I don't think that's a ridiculous amount of work. If you make it bounce 10 times, then you have a lot more work to do. If I make it bounce twice, I have to prove two angles equal 2 different times. One time would look like this, so I basically had to solve for 2 angles every time I do this proof. So in this hole, we'll have to do it twice in total. See, classwork 4 is finding angles 3 and 4. If you make 10 bounces, you're going to be doing it 10 times in total. Okay? So just keep that in mind when you design your project, that there are some cool designs, but I don't know that you really want to make it bounce like 1,000,000 times, because that's why I made the limit 2. I think that 2 is a decent amount of times you have to solve, but definitely not over the top. If you make it over the top, that's kind of your own doing. Okay? So that's kind of the general idea of what we're going to be working on, and this reviews a little bit for you guys the right triangle stuff that you guys were working on before. And again, remember, you get that cushion of air. If anything, our projects in here, I want you guys to understand, I do view them in real life in one sense and not in another sense. Like, do I think you guys are going to go measure creatures or build mini golf holes and calculate the angles? No. If you do, send me the stuff. That'd be great, okay? I don't think that. Do I think there are times in real life when you're going to have to problem solve and things aren't going to fit nicely into the little box that we like put everything in school? Yes, and I feel like these projects are really good examples of like, why am I giving you 4 degrees air? Because real life is a lot sloppier than the stuff we have you guys do on paper. And when you have to get in there and measure things yourself, like, you actually see what like the hands-on experience is like. So please keep in mind that I do think you're building good real life skills. Do I literally think you're gonna go build a mini golf hole? Like, I don't think so, okay? In real life using these calculations. Do I think that you'll do something where you have to problem solve, do a little research, redo stuff, do things that are a little bit tedious and get through some things? Yes. Okay, whether they're mathematical or not, I don't know, but you're getting credit for like a math class in here, right? So like, we put those things in. So try to keep that in mind when you guys are doing the project, okay? So this, again, is multiple classworks. This is today's classwork. It's done. Congratulations. Hopefully you don't need extra time to finish that. If you do, then take the extra time that you need to finish it. Because I didn't